Hello students, welcome to EPG Pathshala. I am Dr. Shashank Deep from IIT Delhi. I am Associate Professor in Department of Chemistry of IIT Delhi. Today we are going to talk on module Energetics and Dynamics of Binding. That module is from paper Biomolecular Interactions. So students, let us see what we are going to learn in this module. We will start with introduction, then we will go to thermodynamic and dynamics of protein ligand binding. The three important things comes into this: enthalpy component, entropy component and heat capacity change. We will also look at the role of water. We will look at approach to calculate the thermodynamic parameters of protein ligand interactions. We will discuss isothermal calorimeter, NMR and computational approaches. So, for most of its function, protein has to bind to its ligand, as we discussed in the last two modules, and they bind through non-covalent interaction. Generally, first we look at the structure to understand the function of a protein. However, sometimes even if interfaces are same, function can be different. And the reason is biological function of molecule is driven by its thermodynamics. Thermodynamics has two components, static and dynamic. So, if we want to understand the molecular mechanism of binding, we need to measure enthalpy and entropy. We need to understand the enthalpy and entropy component of the binding. So, we are going to discuss thermodynamics of protein ligand binding. So, whenever a ligand binds protein, it is accompanied by change in free energy. And as we know that change in free energy has two components, one is enthalpic and entropy. So, protein ligand interaction is simple, a reaction between two species A and B, and as for every reactions, it is accompanied by free energy change, which has two components, enthalpic and entropic. Enthalpic component is also known as static component, and entropic component is called dynamic component. So, delta G is equal to delta H minus T delta S. So, what is enthalpy component? So, whenever a reaction takes place, there is a formation of bond and dissociation of bond. Similar is the case with the protein ligand interactions. Some bonds are formed and some bonds are broken. So, not only bonds between protein and ligand, there are bonds between protein and water, protein and ions, ions and water, and ions and ligand. So, whenever protein binds with a ligand or ligand binds with a protein, few of these bonds are going to be broken and few of the bonds are going to be formed. It is difficult to figure it out just by looking at how many bonds can be broken and how many can be formed. So, whenever a bond is broken, that is an endothermic reaction. So, we need to supply energy to break a bond. Just opposite case, whenever there is bond is formed, heat is going to be expelled, or it is an exothermic reaction. So, total enthalpy change is net contribution from bond breakage and bond formation. Enthalpy can change because of formation breakage of ionic and hydrogen bonds, electrostatic interaction and van der Waals interaction. So these all three different kind of interaction can contribute to enthalpy. Enthalpy is positive. It means that the enthalpy component from the bond formation, bond breakage is greater than enthalpy contribution from the bond. So let's look at entropy component of binding. There are two different kind of entropy component. First is conformational entropy. Generally, binding results into stabilization of particular conformation at the interface, and that leads to decrease in rotation and translation of proteins. That means conformational entropy is decreasing on binding. But this is the general case, not always true. Conformational entropy can also increase on binding. The second component is solvation entropy. Solvation entropy is because of displacement of water from binding interface. So whenever there is a binding, water is getting displaced from either protein or ligand side, and that leads to an increase in entropy. This is well known hydrophobic effect. This figure gives you a typical binding reaction of a protein with ligand. As I told you that binding can be enthalpy driven or entropy driven. So what do we mean by enthalpy driven or entropy driven? So a typical binding reaction can be seen as this. A ligand binds to a protein. Ligand is shown as a rod and your protein is given like this. And there are water molecules around both protein and ligand. When protein binds to ligand, which you can see in the right side, some water is going to be expelled, and that is written as released water molecules. When water is released, it comes out from a hydrophobic surface, it gains entropy. And so, although conformational entropy decreases for protein and ligand, there is net gain of entropy from the release of water molecule. When a reaction happens, we generally know that when delta G is negative, your reaction takes place. Our reaction is spontaneous. But delta G can be negative due to three different ways. When delta G is negative due to entropy component, which is your scheme A, you can see in scheme A delta H is positive. So delta G is negative because minus T delta S is more negative compared to delta S. So it is entropic component which makes delta G negative. And that's why this scheme A is basically for entropy driven process. You can see scheme B, again delta G is negative, but now delta G is not negative because of entropy component. It is negative because of enthalpy component. And that's why this type of reaction is called enthalpy driven reaction. There is another kind of scenario possible when negative is because of both enthalpy and entropy. In that case, it is both enthalpy and entropy driven binding. Heat capacity change. This is another important parameter, thermodynamic parameter, which tells about mechanism of the reaction. The thermodynamic quantity which dictates the hydrophobicity of interaction is your heat capacity change. By looking at heat capacity change, what can we tell? Generally, when hydrophobic surface is buried during protein ligand interaction, this is accompanied by large negative heat capacity change. A positive but a small heat capacity change is also observed for polar surfaces which is buried in non-polar environment. By measuring heat capacity change, we can know how much solvent accessible surface area changed during the binding, since the changes in solvent accessible surface area upon binding is related to heat capacity of binding. There is a role of water. They play a very key role. If you take a hydrophobic surface, water is believed to be in partially frozen state. What happens basically is, to maximize its hydrogen bonding with hydrophobic surface, water chooses to be in only few of the conformations, and that basically is known as partially frozen state. Now, if you take out that water from the surface, you are basically increasing the entropy of the water, because now water is more free. It is no longer in partially frozen state. And that's why exclusion of water from these surfaces to the bulk has favorable entropic effect. Many water bonds with protein or ligand need to be broken during the ligand binding, and that has unfavorable enthalpic effect. Now question is how to calculate thermodynamic parameter for protein ligand binding. As we know, it is very difficult to know what is the enthalpy change, since lot of bonds are getting formed or broken during a protein ligand interaction. So one of the best method is to measure experimentally, and the instrument which we use is isothermal calorimetry. The calorimetry is the technique that determines the accurate thermodynamic parameters for protein ligand interactions. It can be of different type, flow or batch calorimetry. This shows, the left hand side shows you a typical thermal profile obtained from isothermal calorimeter. So on y-axis you have microcal per second, and the x-axis it is time. So basically in isothermal calorimeter, we add ligand to the protein solution during a particular, after a particular interval. So you can see in the picture the first injection. During the first injection you get a thermal heat absorbed or heat release will be plotted. Then again there is injection, and then you see how much heat is absorbed or released during a particular injection. That is converted to kilocalorie per mole versus molar ratio curve, and the typical curve is given in the right hand side. The difference between the maximum on the y-axis and minimum on the y-axis is basically delta H. So enthalpy can be, ITC is a typical profile which can give delta H, delta S, delta G in one shot. So now see how we can calculate delta S. The slope of this curve, slope of this your linear curve at the molar ratio in between, you can that gives you a binding affinity. That gives you binding affinity, and this growth, at the middle, will be related to molar ratio of the stoichiometry. So from one curve you get delta H, delta G, since you know binding affinity, and if you know delta H and delta G, you can calculate delta S, and also you can get the information about stoichiometry. What are the other techniques? A spectroscopy technique is another way to calculate thermodynamic parameter. It is an indirect way to calculate thermodynamic. From a spectroscopic technique, we can calculate Kd as we have seen in the module. And we know that Kd is related to delta G, so we can calculate delta G naught using equation minus RT ln Kd by C. So through a spectroscopy, first we measure delta G naught. Now question is how to measure enthalpy and entropy. Enthalpy and entropy can also be measured by measuring delta G naught at different temperatures. And the equation given is delta SD is equal to D delta GT by T, D1 by T. So if you plot delta G by T versus 1 by T, the slope will give you delta H of binding, enthalpy of binding, and since we know delta G, delta H measurement can also give you delta S. So entropy can be calculated using free energy and enthalpy. NMR is another important technique to understand protein ligand binding. Generally, if we want to identify the binding region, NMR is only technique which can give you residual level information. Chemical shift mapping is generally used to identify the binding region. The perturbation in chemical shift can also be used to calculate the binding free energy and binding constant. There are a lot of advantages of NMR over other techniques. One of the most important advantage is it can measure occupancies of individual binding sites and hence can be used to determine microscopic binding constant. Once we know the free energy, we can also calculate entropy and enthalpy component by measuring temperature dependence of free energy. NMR not only helps in measuring entropy, it can also tell you about the contribution of conformational entropy change to total entropy. And this is generally been done by measuring NMR relaxation parameters. So NMR can also be used to calculate conformational entropy component. And the way we do it by measuring T1, T2 and NOE. T1, T2 and NOE is related to a spectral density function, and the equation is given by for R1, R2 and NOE is given in this slide. So R1 depends on your spectral density function of omega h minus omega n, the spectral density function at omega n, a spectral density function at omega h plus omega n, and again a spectral density function at nitrogen frequency. Similarly, R2 is dependent on J at 0. The spectral density is given here as a J. So J as 0, J as at omega h minus omega n, J at omega n, J at omega h, J at omega h plus omega n, and that also has REX component. And similarly, NOE is given by these equations, where D depends on your gyromagnetic ratio of N, gyromagnetic ratio of H, and your distance R and H. previous slides gives you some equations where mu naught is permeability of free space, H is Planck's constant, gamma n and gamma h are gyromagnetic ratio of 1h and 15n, omega h and omega n are the Larmor frequency of proton and 15n, and delta sigma is chemical shift anisotropy measured for 15n, which is around minus 160 ppm. Now you can see that formula for T1, T2 NOE contains 5 spectral density values, so a direct solution of equation is not possible since only 3 measured values, that is T1, T2 and NOE, are available. To solve these 5 equations, Lipari and Szabo came with model-free formalism. What I am going to discuss is modified model-free approach, which is given by Mandel. In this case, spectral density can be expressed in terms of SF and SS, tau F, tau S, tau M. And this is the equation: J omega is 2 by 5 S square tau M divided by 1 plus omega tau M square plus 1 minus SF square. And similarly, you have 3 different terms where tau F is given by tau F into tau M, tau F dash is given by tau F into tau M divided by tau F plus tau M, tau S dash is given by tau S into tau M by tau S plus tau M, where tau M is isotropic rotational correlation time, tau F and tau S is effective correlation time for internal motion on fast and slow time scale, and SF and SS is order parameter for the internal motion on the fast and slow time scales. Dynamic component of free energy can be calculated from relaxation parameters using model-free formalism. What we do is, first we calculate global rotational correlation time. This is generally done by excluding the residues first, for which internal motions are very fast, and that we can guess by looking at R2 by R1 value and NOE value. If they are low, we can simply exclude those residues. The second is the residues which are experiencing conformational exchange at a slow time scale. Now, global rotational correlation time of the molecule is estimated by fitting iterative trimmed R2 by R1 value ratio to an isotropic tensor. And finally, data is fit to 5 different models of the local motion for each residue to get the information about various order parameters, correlation times and rate of exchange. So order parameter can be calculated from modified model-free formalism. We generally do it for NH or CH bond vector. This order parameter gives you an idea about mobility of that particular vector. Its value ranges from 0 to 1. If the value is 1, it means we have completely rigid vector. So if we talk about order region of protein, it is generally high, it is 0.85. When you go to disorder, since they are more flexible regions, so mobility is high and order parameter is in the region of 0.4 to 0.6. Order parameter is correlated with conformational entropy, and by measuring order parameter, we can calculate delta S. So delta S, that is conformational entropy for AB, means you are going from A to B state, can be given by equation R sigma K ln 1 minus SBK square divided by 1 minus SAK square. We can also calculate side chain conformational entropy by equation delta SAB R sigma CM sigma SBN square minus SN square. Where Cm is the function of number of side chain dihedral angle in a given residue type, and a fit parameters and sums run over all residues N of type M. Conformational entropy can also be calculated using this equation. Delta S by Kb is equal to 0.88 N residue delta log 1 minus order parameter for NH square, average of delta multiplied by 0.88 into N res minus 0.56 N chi, and average of delta order parameter for axis square. N res is total number of residues, N chi is total number of side chain chi angles. Average of delta O axis square is basically the measured average change in methyl axis order parameter, and delta ln 1 minus ONH square is the measured average change in amide order parameter. Can calculate thermodynamic parameters using computational approach. Not only gives insight about contribution of different interactions, but also it can tell you about the contribution of conformational solvation entropic free energy to total free energy. Generally, docking is quite often used to predict binding affinity. That gives you enthalpy component. To study the dynamic behavior of protein, the different methods based on force field calculation are employed, like molecular mechanics, molecular dynamics, and Monte Carlo simulation. These methods determine the configurational entropy change. There are several different MD-based approaches. One is free energy perturbation method, thermodynamic integration method, lambda dynamic simulation, molecular mechanics, Poisson-Boltzmann surface area method, linear interaction energy, hybrid quantum chemical mechanical approach. So there are different approaches given by different scientists, and that not only calculates entropy, but it can also tells you about contribution from solvation and conformational changes. So, students, let us now summarize what we have learned in this module. First, very important point, that biological function of a molecule is driven by its thermodynamics, which is energetics. It has two components, static and dynamic. The enthalpy contribution to the free energy is basically due to formation and breakage of bond. Binding is favored if there is a net decrease in enthalpy. The entropic contribution, on the other hand, is due to the loss of degree of freedom on binding, that is conformational changes. And second is displacement of water from the binding interface, and that is hydrophobic interactions. Water plays a very important role in protein ligand binding. The enthalpic entropic component we can measure either by isothermal calorimeter, NMR, or a spectroscope. NMR and MD simulation help us in understanding change in dynamics on ligand binding and in calculating the conformational entropy change. Thank you.